Okay, you ready to go?
I'm ready to go.
All right, I'll post it live.
So everyone, welcome to our Hangout. We are in the process of sharing our Hangout with all of you who are tuned into Google Plus at this very moment so that you know to click into our chat room.
It always takes us a second, right? When we start up a new Hangout, we have to take a second then to tweet it and Facebook, and not that anybody uses those anymore, but
But in case some of you do.
Yeah, exactly. So it just takes us a second.
So this is our 247th episode. We have almost hit a quarter of a kilo Astronomy Cast, which is just fun to say, actually.
Is that a universal form of measurement?
Kilo Astronomy Cast? It should be.
Okay. I have tweeted it. I will Facebook it. And then we'll talk.
That sounds great.
It's got to be super boring. Sorry. I have paid my debt to society now, so I'm good.
That works.
All right, and then I can look at the Hangout itself. All right. Now, if you want to, the way we normally do this, if you've never participated in one of our live episodes of Astronomy Cast, what we do is initially we'll just record the show as scheduled. And so today we're going to do episode 247, which is called The Ages of Things. And then when that's done, we will then open up the Hangout. We'll post a link to the Hangout itself into the comment thread that's attached to this episode, this live stream that you're watching right now as the Google Hangout. And then you can then click that link, and 6 people, 8 people can join us in the Hangout and ask us questions and tell us stories about their astronomy and things like that. And we sort of keep it fairly fast and loose. The other thing that's really interesting is if you're watching this right now, there's a really cool extension to Chrome called Better Hangouts on Air, and this was actually created as a way to sort of help Astronomy Cast and other on-air podcasts be a little cooler to watch. And so if you install that extension, you get a few a little drop-down box when the Hangout is happening live, and you can maximize the window. You can open up the video stream in a new tab, and then you can press F11 and you just get a full-screen video. I'm not sure that's what you want. And you can also embed the stream into some exterior website, which we really should be doing, but I think that would kill more time. So
that's on my list of things to program to have happen automatically as part of the
one button. Yeah, exactly. We press one button and everybody.
There.
Okay, all right, good, cool. And then it sort of goes into all these places around the world. So that sounds perfect. Tweets,
hopefully
and Facebooks,
a week and a half from
Tumbles, and stuff like that. That's great. I love the fact that you're also a programmer. So that's really cool. And an artist. So, and so where are you right now, Pamela?
I'm down in Austin, Texas at the 219th meeting of the American Astronomical Society. I'm only here for 2 days, so if you want to hear the whole meeting get reported, follow the hashtag #AAS219 on Twitter. I haven't actually spotted anyone else using Google Plus yet, and I'm hoping there's others out there, and I just haven't found them. It's a meeting where there's going to be all kinds of science, everything from neutrinos to planets to dark matter to dark energy to more exoplanets. And I unfortunately am stuck in a lot of business meetings, but I'm going to do what I can to bring the press releases to everyone via Google+.
Yeah, and for those of you who don't believe that Pamela's in a different hotel every week, I'm sure someone should actually put together some kind of animation of every single Pamela background, and then we can get this really cool animation of all the different places that you always are.
Well, one of the things Fraser and I are going to be working on doing is getting our recording schedule back on track so that unless I'm on a plane in the air, which is happening Wednesday, we're going to be recording on Mondays and Wednesdays. Now, I'm in the air on Monday or Wednesday often enough that recording both those days when I'm in town will just barely keep us caught up. But you now know our plan.
Right. And so one of the things that we've done is I've added to Universe Today, I've added on the sidebar of Universe Today a countdown that shows you how long it's going to take until we do our next recording. And we're actually doing 2 recordings now. There's this, where we do Astronomy Cast live, and then there's the other we're calling Weekly Space Hangout, unless someone can provide us a better name. Which is the one that we did back on Thursday, and that's where it's me and Pamela and Phil Plait and Alan Boyle and Emily Oktawala and Ian O'Neill and lots of people from our ecosystem of space journalists, and we can kind of do a roundup, and that's the opposite of Astronomy Cast. And this is the question that a lot of people have is, why don't you really cover any of the breaking news that's going on? And that's sort of what Astronomy Cast is not about. We want these episodes to be timeless, but we totally understand that we also want to, talk about all the crazy stuff that's breaking, and so that's why we've got this other format that we're trying out. The other thing that we've been doing that's been really neat is we're doing these virtual star parties. So we've been connecting telescopes right into a Google Plus Hangout, and then just live broadcasting the view from the telescope, and sometimes it's me and Phil, or Pamela and me and Phil, and we're all just sort of we're talking to the astronomer and sort of seeing what we're looking at. And the plan is we're going to get multiple telescopes and actually, again, do this on a fairly regular basis. And you can kind of see how the different telescopes give you different views of the sky and what the different capabilities are. And it's been really quite exciting, actually. I really enjoy it. And we're going to probably do some more tests. So we're still just in testing mode. We're probably going to do 2 or 3 more tests, probably even just this week. I've got a bunch of new astronomers coming online. So, but if you're an amateur astronomer and you want to participate in the Hangout itself, the best thing to do is or what you need to be able to do is if you have a telescope and you have some way to get the view from your telescope into a computer, then you can totally help us out. Now, in some cases like Celestron and Meade and Orion, they'll have some they'll have a CCD, or they'll have, like with Celestron, they have the next image, or some people have taken they've taken just the webcam and they just stick it right next to the eyepiece and they can get a view. And other people have
to take apart your webcam to do this. So.
Yeah, you have to remove the IR filter, but there's instructions on the internet. But people have done this, and other people hook up nice big DSLR cameras with this crazy mount to the telescope and view it that way. And with all of these, what's important is that you have a view on your computer of what's being seen by the telescope. And if you can do that, then it's really easy to get that view from your computer into the Hangout. And like I said, what we're trying to do is make this really just feel like a star party. Like we're just walking around and we're looking at telescopes and talking to the astronomer and like, let's look at this over here and then let's look at that over there. So that's all been really exciting, and I'm quite looking forward to doing more of this. So, but those are totally impromptu, and they show up randomly right now while we're testing. So. Okay, cool. Well, then, are you? And again, there should be sort of one thread where all the comments are going to go, and when sort of if you have any questions or comments, this is the place to put them, and then we'll, sort of either answer some questions at the end of the show, or we can, or you can just jump in and ask us your questions personally. And that's what we kind of want to have. We'd prefer to have people who jump into the Hangout and actually interact with us and ask us some questions, as opposed to sort of watching in a different way, right?
Yeah.
So if that makes any sense. Andreas says it would make it global, so have images from all the time zones. And that's the plan, right? Is that we can have one person in Pacific time looking at Venus just as the sun is going down, at the same time that we can have someone on the East Coast looking at Jupiter when it's nice and high and bright, someone in the southern hemisphere, someone in the daytime looking at the sun, and we can kind of do it all at the same time. So it's right now we've got this, I think, licked. So I'm looking forward to it. Okay, so why don't we get set and do our recording, and then when we're finished that, we'll then open it up. I'll post a link into the thread, and then you can all join us. The other thing you can do is you can catch our mistakes.
Yes.
And we make them. We make pronunciation mistakes.
That's me, not him.
And we make, but we also, we also will make just, sometimes scientific factual errors, and sometimes we will just forget things that should be in the show and sort of cover under the topic. And so I'll keep watching the comment thread, and if you realize that I've made a mistake, or if there's some aspect of this topic that maybe we should talk about or didn't even think about, I'm more than happy to inject that in and sort of incorporate that into the show as we do it. So there's a real feedback to what we're doing, generally, and that's really great.
And if you see us looking all over the place, it's because our cameras are not attached to our computers. And then, so there's I'm looking at Fraser, I'm looking to make sure my audio levels are correctly, I'm looking at your audience, and I'm not trying to look like some crazy possessed senator who doesn't know where the camera is.
Yeah. Yeah, exactly. All right. Okay. Well, let's get rolling then. So, are you ready to record?
I'm ready to record. Tell me when you're pressing the button.
Okay. I've already done a sound check. Let's see. Okay. Testing. Yep. Looks good. You ready?
Yep.
Okay. Here we go. Astronomy Cast, episode 247 for Monday, January 9th, 2012. The Ages of Things. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hi, Pamela. How you doing?
I'm doing well. How are you doing, Fraser?
Good. And where are you this week?
I am in Austin, Texas, at the 219th meeting of the American Astronomical Society.
That's good. So you were like buried in space news.
I am not only buried in space news, but I'm among my people. It's a good place to be.
Your people, right, with your flock. That's good. All right, so this is going to be one of those how we know what we know kind of shows. How do scientists determine the ages of things? How do we know the age of everything, from stone tools to the age of the Earth to the solar system to the age of the very universe? All right, Pamela. So I think that was sort of the plan here, was that we're going to sort of explain to people how we know what are the various measuring sticks, age measuring sticks that astronomers use and scientists use to figure out how old everything is. And I thought, well, why don't we start kind of close to home and think about when scientists discover some civilization, they discover stone tools, they find an archaeological dig. How old is everything that was in that dig? How do they know how old that stuff is?
It all pretty much boils down to radioisotope dating and looking to see what's in what sedimentary layer. One of the things that is a blessing and a curse, and I say a curse because it leads to cancer now and then, and that's never a good thing, is a variety of the atoms that get created in supernovae and through other high-energy processes aren't stable. And they're not stable on varying time scales. So some things, it might be you set them on the table and say you have 1,000 atoms. Well, you wait an hour and you have 500 atoms of what you started with, and 500 atoms of what's called a daughter material, a daughter atom. And so you can actually look to see how much, what the ratio is between these two different atoms, and based on the ratio, you can see how many half-lives have gone by. Now, if you have something that decays quickly, that's only good for time dating something in the recent past. I know as a small child, I was nerdy enough that I knew about carbon dating, and I was terrified that my teachers would use the carbon in my pencil to figure out I didn't do my homework on time, because I was that kind of a nerd and lacked the level of understanding I needed.
Or overestimated the abilities of your teachers.
Exactly.
Yeah.
But the thing is, carbon doesn't decay on that type of a time scale. So we can only use carbon dating to date things in the distant past. We can use other forms of dating for the recent past. And through all the different atoms that we have that decay on the time scales of minutes to hours to days to weeks to years to centuries, millennium to millions of years, by combining all of these different types of radioisotope decay, we're able to very carefully measure the age of different materials that contain these radioactive processes. And
so do scientists have these overlapping methods of radioactive decay, and can they go from really, really short events all the way to the age of the universe? I mean, are there any gaps
Yeah.
in this?
Well, so in general, things that decay quickly are also things that we have to generate in cyclotron laboratories. So it's not like there's piles of polonium-120 lying around.
Yeah.
So for the most part, the way we get to the things that we can radiocarbon date and other things like that is we have to go through the archaeological record. So you look for those points where you're able to bridge from our known understanding of humanity to, aha, I found a radioisotope that has decayed in a useful manner. And then from there, we just bridge our way backwards. And we do look for the times where we find in materials more than one of these different radioisotopes and just keep building our way backwards.
And where does it sort of fall apart? I mean, does each isotope only give you so much, and then it's just not useful anymore?
Yeah, it's a matter of there's just not going to have been enough left at the end of the period. It's you go halfway to the wall, halfway to the wall, halfway to the wall, and never actually make it to the wall. At a certain point, you have run out of atoms to decay. So you eventually get far enough back in time that the sample you're looking at has completely decayed into its daughter atoms.
And I guess you can imagine that's kind of like you're looking at like ice melting, and you've got a piece of ice on a plate, and it's in the living room, and you're looking at it, and it's unmelted, and you go, well, that ice clearly was brought out just seconds ago, and then it's kind of half melted, and well, it's been within the last less than an hour, but more than a couple of minutes. But if it's just water, it could have been there for decades.
Exactly. Well, not decades.
I know it evaporated. I know. I realized as I said that. But okay, great. So then, which is the tool that they would use? We went back to my first example, right? We're going to take a look at stone tools left by Neanderthals. What is the method that they would use to date that kind of thing? Human civilization stuff.
So this is where we often use carbon-14. It's a naturally occurring radioactive form of carbon, and the nice thing about it is human beings tend to pick it up, plants pick it up, all of us, we're made of carbon, and so we become partly radioactive in the form of carbon-14, and so you can look at the leftover logs in fire pits. You can look at the leftover carbon in the bones, and you can start to get at how old things are. Carbon-14 has a radioactive half-life of 5,730 years. So you can basically step back in these intervals of thousands of years, tens of thousands of years. In fact, we think the limit for using this is actually somewhere around 60,000 years in the past that this starts to become a not entirely useful way of studying the age of things in our environment. And
so what will the carbon-14, what will it decay into? Or are they determining the number of carbon-14 atoms that are left? They're measuring like the ratio of carbon-14 to what it decays into, right?
Yes. So they look at the ratio, and this is where people who are watching this video get to watch me realize I don't have the daughter isotope on my screen, and I'm going to ask Preston.
Do you want to?
Yeah, we're just.
Do you want to re-ask the question, or do you want to? You still there?
Yeah, I'm still here.
Okay,
I'm just looking at my screen and realizing I totally don't have that number on it.
You don't have that number in front of you?
No.
Why don't I re-ask? How about I re-ask the question, and we can kind of, and then so it doesn't have to be so specific on the facts.
Okay.
Welcome to the reality of recording Astronomy Cast.
I do not know the entire.
I know. How could you not? All right.
I know. I'm a horrible person.
Yeah. Okay. So do you want me to re-ask that question? Is that okay?
Yeah, go ahead.
Okay, well, let me see that. All right. Right, okay, so then you've got the quantity of the carbon-14, and then you're gonna be able to measure that ratio of what you had carbon-14 and the various daughter elements that it's going to decay into and get a sense of how old it is. Okay, so we've done then carbon-14, and you say that sort of. How early can we measure with that? Within a few hundred years, right? And then.
Well, a few hundred years starts pushing it because you haven't had that much. I mean, its half-life is 5,730 years, so a quarter of it will have decayed in 2,600 years, and so you want to get closer to the 1,000-year mark than the couple hundred-year mark.
Right. So definitely 5,000 years is is great, but
Yeah,
you
that's a
don't want
comfortable
to be
place to
measuring
be.
beyond 60,000 years. Okay, all right.
Right.
Well, so then let's take so then the next age of something, I would assume, is going to be like rock formation, lava flows,
Yeah.
things here on Earth that we're going to try and date.
So we also look at things like the uranium to thorium dating method, which
Mhm.
looks at uranium-234 decaying into thorium-230. And this is something where we're looking at processes that, depending on where we are in this, there's a whole network of things in this that decay. We're looking for that combination at a half-life of 80,000 years. But we can also look at uranium-235, which decays into the generally not talked about in chemistry class, protactinium-231, which is a half-life of 34,000. So by looking at these different decay paths and looking at their different daughter processes, this is where we can start getting into more of the geologic record, getting back into the hundreds of thousands of
Right.
years over the course of their decays.
And same thing, like if they're going to measure soil, I'm trying to think like soil sediments or
Right.
ice cores, things where you're looking at hundreds of thousands to millions of years old. And so you're telling me there's little bits of uranium kind of everywhere
Well,
for the
yeah,
measuring?
it's actually a really good thing because it's part of what keeps our planet warm. Our planet is a lot warmer than it would be strictly from having sunlight hitting it and an atmosphere that blankets it and keeps some of the IR radiation trapped in. Our planet's internal temperature is driven by the constant decay of radioactive particles. It provides heat, and that's a good thing because heat helps provide life. So be glad for the radioactive materials.
Right. So then how, I mean, you can keep pushing that further and further back, but I can imagine,
Yeah.
if the whole surface of the Earth is being resurfaced thanks to plate tectonics
Right.
and such like that, there would be no way to get figure out how old the Earth itself is. And yet we
Yeah.
know quite precisely how old the Earth is. So how on Earth did astronomers figure that one out?
Well,
Geologists.
I mean, we
We'll
do
let the geologists have
actually
that discovery. Yeah. Right.
we do actually look for progressively older and older rocks, and we do find rocks that are billions of years old, and this is where we start pressing ourselves backwards with things like looking at samarium and nabibium, neodymium rather, and their decay rates, which get us back to millions of years, 2.5 billion years. So we do have some pretty old rocks, but you're right, we are still pushing the billions of years limit. So we look at sedimentary histories, we look at the way things are capable of moving, and then we start looking at cratering histories on other worlds, and we start grabbing asteroids. Asteroids are really, at the end of the day, the final authority on the original chemistry and the age of our solar system. So we wait for asteroids to actually come to us. We call them meteorites by the time they reach the surface of the planet, and take them to labs. And this is part of why scientists are so avidly collecting meteors. And while we know that lots of amateur astronomers on your shelf as a trophy object, that's actually a piece of data that hasn't been collected that you're keeping on your shelf.
And so the theory goes that if you're going to find a meteorite and determine how old that meteorite is, then you're going to know how old the Earth is? I don't
Right.
understand.
So the idea is the entire solar system formed at once. And so the age of the Earth is the age of, well, not the moon. It formed later. It's a blasted off piece. So that it's sort of like its materials formed at the same time, but it was part of two other things. But all the materials came together, maybe not in the same structure they're in now. Big asteroids have broken apart into smaller asteroids. Things have hit each other, creating the Earth's moon. But all of the stuff in our solar system formed out of the same solar nebula, formed at the same time. And so if you can age a meteorite, you've aged the entire solar system. Now, the more of these that you age at once, it's like taking more and more measurements. You're able to get a more and more precise understanding of the age. So this is where we're constantly trying to catch and collect and understand asteroids.
And was this always assumed to be the case, or were astronomers not even really sure that that all of the meteorites were going to be the same age? I mean,
well, it was one of those things where you postulate it and hope it's true. And as we've measured it, it's come out to be we're able to put very good limits on the age of the solar system using meteorites.
now you hinted for a second there that astronomers use cratering on places like the moon, and I know on Mars and stuff. They'll use that as a completely different method for determining the age of things. So how does that work?
Well, so there's two different ages that we worry about. One is when did the stuff form, and then the other is when did the surface of the stuff form. So when you look at the Earth, our surface is extremely young. In fact, there's volcanoes, you look at bits of their surface, like Etna's going off, I think earlier this month, and that surface is measured in days. The only way we have, since we can't readily go there all the time, of getting the age of the entirety of the surface is to look at cratering histories. And this is where we actually try and engage the public's help, because we want to measure the ages of as much of the surface as possible so we can start understanding what was the collision history in the past, what was the bombardment history in the past. And we create projects that ask you to help us train computers to more effectively measure craters for us, because let's face it, at the end of the day, measuring craters is fun for a while and then you want to do other things.
Right.
But we also ask you to measure craters for us.
Right. This is a project that you're actually working on, right?
This is, and you've been giving us server advice. So we're launching a new project called Moon Mappers with CosmoQuest, which Fraser and I have talked about a bit in some of our other hangouts. And CosmoQuest is a community where we're hoping that you'll come and learn like you do with Astronomy Cast and listen to Fraser and I, and then apply all these things that you're learning to actually doing science. And Moon Mappers is our very first science project. It's part of the Lunar Reconnaissance Orbiter mission, not the orbiter itself. And we're asking you to help us correct crater finding algorithms, to go in and tell us where does the software screw up and fix their outputs, and to help us measure the age of various surface features on the moon.
This episode of Astronomy Cast is brought to you by Cosmosphere. Sorry, I got to re-record that. Hold on a second, because I said it wrong.
Yeah.
So this episode of Astronomy Cast is brought to you by CosmoQuest. We're sponsoring ourselves or something.
Something like that.
Yeah. Right? But no, yeah, I mean, our goal has always been to get everybody involved in space and astronomy to some degree, and we're trying to, Pamela's been working with NASA and other science agencies to get data from the spacecraft and then bring in the general public to help in actually creating science that then gets used for real scientific research that may not even be possible to be done. And so this is one of those projects, and now we've got this umbrella organization where we can and sort of server and hardware and software and stuff that we can actually do more and more of this. So hopefully you can hear a bunch more of these kinds of announcements and more of these projects as we go on, and we'll recruit as many of you as you can to do some real science. And as we move forward doing this, we're going to be working to determine the ages of different features on the asteroid Vesta. We're working with the Dawn mission. On the surface of Mercury, we're working with the Messenger mission. And in all of these cases, what we're doing is we're looking for those places that have extremely few craters. Those are the young surfaces. We're looking for those places where you have crater bombarding on top of crater, crater inside of crater. These places that are extremely rich in craters, those are the old places. And then we're looking to see, okay, can we trace this area that's almost devoid of craters and thus actually trace out where there was a tongue of lava from an ancient volcano or a more modern volcano. We're trying to understand what is the geologic history, how recently were there volcanoes active on the moon. That's something I always am startled by, is there was actually volcanism on the moon. Imagine what that must have looked like to the amoebas swimming around on the surface of the planet not paying any attention. It was an amazing past, and we can better understand that past by all of us working together. But how accurate is this method of determining the cratering? I mean, I've heard astronomers say, well, you can see that region of the Mars is 1 billion years old, or this part is very active and is 1 million years old. But how can they know that this amount of craters is 1 billion and that amount of craters is 1 million?
It gets tricky, especially since the cratering rate isn't constant with time, and we don't know how it varied with time. And so right now, what we do is we bridge together the different periods using actually moon rocks. So the astronauts, when they went to the moon, and the spacecraft, mostly Russian, that when they went to the moon and brought back rocks, they brought back rocks from a variety of different terrains. They brought it back from nice young areas. They brought them back from older areas. And from each of these rocks, using the radioisotope method, we were able to determine this area with this cratering rate is this age. This other area with this other cratering rate is this other age. Now, the problem that we run into is we've only done these sample return missions for the moon. We want to do them for Mars. This is part of the plan of the Mars C mission that's planned for the next decade. We want to do this with asteroids. And right now, we're sort of making assumptions. We're saying, okay, so we think some things happened earlier on Mars, it's further out. Some things happened later for Mercury, it's further in. So we're making rough corrections to what we know based on the moon, based on theoretical models. But for the most part, we're within a few 100 million years, which isn't entirely a comfortable place to be. But that's the best we can do until we bring back enough rocks to say, okay, this type of terrain is this, period. We're done for the entire solar system.
Right. I can see that it's sort of a part of the process is that the astronomers have they've got pretty accurate measurements on the moon, and they've been able to sort of correlate the cratering with the moon rocks that they're bringing back, but then they're taking that cratering estimates and they're using that as a measuring stick for other parts of the solar system, but they haven't backed it up yet with actual samples, which is, you know, hopefully going to come within the next few decades. Okay.
Yeah.
All right, so that's enough sort of stuff in our solar system. Well, I guess there's one more object in our solar system we should probably take a look at, and that's the age of the sun.
Right.
But obviously we can't grab parts of the sun, and we're making a pretty big
dangerous.
We're making a pretty big assumption that the sun formed at the same time as the planets in the solar system. So how do astronomers know this?
Well, so at a certain point, we do assume the sun formed at the exact same time as everything else in the solar system. But moving beyond that, we also look at stellar evolutionary theory models, where we say, okay, the sun is this size, it had to go through this in the past, it took it this long to get to the stage it's at now. So that's one way of doing it. And then where we can, we also use, well, in this case, instead of radioisotope dating, we call it cosmochronography. And this is where we actually use the exact same idea, but with different types of elements. For instance, strontium is one that gets used when we look at, or scanadium are elements that get used when we start looking at stars and figuring out, well, how old is that? So there's a whole variety of different isotopic combinations that can get us giga-years of age.
Right, but we can't take, again, a piece of those distant stars, stick them in our, gas chromatograph and, get the age. Like, what is the method that they use to determine even just the chemical elements in those stars? How do they do that?
So the nice thing is that the sun is actually in some ways a gas chromatograph for us. One way that you can determine the composition of things here on the planet Earth is you burn them and you look and see what emission lines are present in the heated up materials, and you create spectra and use the spectra to get at the composition. Well, the sun you don't exactly need to set on fire, it's kind of already there. So when we look at the sun, all of the atoms in its outer atmosphere, depending on the exact energies, are either emitting wavelengths of light that we can see as spectral emission lines, or much more commonly, they're sitting there absorbing out radiation and creating atomic absorption lines. And by measuring the depth of these absorption lines, do they absorb all the radiation in a given wavelength of light? Do they absorb just a little bit of the light in a given wavelength? By looking at the depth of the lines, that tells us how much light has been absorbed, and a variety of other things like what are the ratios at different temperatures. We can get at the temperature of the star, and then we can get at the surface gravity of the star, and then we can get at the abundance of materials within the star. Unfortunately, it's a three-variable problem, and you have to solve for all three variables, which can get really annoying. But when you're done, you know exactly what a star is made of.
And so by again measuring the ratios of those various elements which are known to decay at very specific rates, you can determine how old that star is.
Exactly. So here we again still use uranium. In this case, we're looking at uranium-238, which has a half-life of 4.47 billion years, and it decays into lead-206. We're also looking at rubidium, which has a 48 gigayear life. We're looking at aluminum, which has a 0.75 mega-year half-life. So we have all these different atoms that we look at, and by looking at all these different combinations, we're able to fine-tune to get a good sense of how old things are. Now, the only problem with this is you have to be able to get extremely high-resolution spectra to see all these different lines. And to get high-resolution spectra, you are somewhat confined to only looking at the brightest stars, and to a certain degree only using the biggest telescope. So it limits how far away you're able to use this method.
Okay, fine. But how do astronomers know how old the universe itself is? You know, because I mean, you can't go and grab little pieces of universe stuff at the Big Bang, you know, and measure its age. So that's got to be the final, ultimate challenge. How on earth do astronomers determine just how old the universe itself is?
Well, for the universe in general, because that's such a controversial number in so many ways, we need to have multiple lines of evidence. So the first thing we say is no star is allowed to be older than the universe. That would just be silly. And so we just look at the oldest stars and use stellar evolutionary theory models, and we're able to figure out from the cooling of white dwarfs, from how long it takes stars of different masses to become red giants, that globular clusters, which are the oldest collections of stars in the universe, are 12 billion years old, give or take. So we know the universe is more than 12 billion years from looking at the stars. And then beyond that, we have to start looking at cosmological models and matching the predictions of those models to what we see when we examine the cosmic microwave background and the evolution of structure in the universe. And from using the WMAC, the Wilkinson microwave anisotropy probe, we're able to study what was the distribution of hot spots and what was their size on the cosmic microwave background radiation. And we've done entire shows on this that you should go back and listen to.
One whole episode just on how old the universe is.
Yeah. So go back and listen to that. But it boils down to a whole lot of scary, complicated math and geometry, more to the point, that tells us our universe is more than 13 billion years old. So the stars and all of the fancy calculations using the cosmic microwave background all get us to the same place, and it's all consistent with what we see from radioisotope dating.
And now we have that really precise number. I mean, now we know it is 13.75 plus or minus 0.17 billion years old.
And they just keep adding new decimal points.
Exactly. That's right.
Better.
Yeah, and so each, as successive versions of the, these surveys of the microwave background radiation come out with more sensitive instruments, they'll just keep adding decimal places. But we're pretty confident about the 13.7 part.
Yeah.
That's really cool.
So we live in an old universe on a fairly young planet, and we're still at the beginning of the universe, but we're at the most interesting time, and so all of these techniques have ganged up to give us a consistent result, and they'll continue to work into the future, and it's just one of those neat things to see the pieces building together.
That sounds great. All right, well, thanks a lot, Pamela.
My pleasure. And this is the part of the show where we
save.
And now we will start flipping over to look for your questions in the comments,
and I'll
while we close out before we do something bad.
And if everyone could do one other thing as well, which is if you can +1 the post that you're watching, because we actually have no way to know how many people are watching this episode compared to anything. They don't tell us any viewership numbers, which is too bad. And so the thing that we do is we beg you to click on the +1 and then and then we can kind of see what the total number of people watching live is. The other thing to do, okay, so I'm going to post the link in the comment thread now, and then people can jump in and actually join the Hangout itself, and hopefully the point of this here is you can ask some questions and interact with us. The other thing you can do is you can ask any questions you want in the comment thread, and I'll just keep looking through the comment thread and find any questions that I like, and I'll pose it to Pamela, and we can go from there. So if anyone has any questions. Jeff Borst says that Pamela needs to paint continents and clouds.
And I'm flipping through the comments list,
yeah.
This is why you're seeing my face react.
On your Smurf spit cover, which I think is a great idea. Oh, and if you are going to jump into the Hangout, you'll want to make sure you've got headphones on or some kind of noise cancellation method, because otherwise we get this echo that pops into the Other thing you can do is you can ask any questions you want.
Oh, nice. I'm hearing Fraser echoing with like a 3-second delay.
Well, that's the other thing is if you are going to jump into the Hangout, you need to stop the live stream, because then you get the echo of the live stream that then gets pumped back in. So.
Yeah, that was me. Sorry about that.
Hi, Owen. How's it going?
Fine. How are you?
Good. So, do you have a question for us, or?
No, not really.
Well, welcome to the show.
Welcome to the show. And if anyone has, and so people were wondering why you can't join the Hangout beforehand, because I only invite Pamela into the Hangout that we're having, and then it's at the end of the episode we'll actually then open up and provide the link, and other people can join us and jump in and ask questions. And if you can give us some feedback on the format, I mean. Yeah. We're trying to, we're experimenting with this. I know the audio quality doesn't sound really great for people listening, and that's more just has to do with what the Hangout on Air broadcast quality sounds like. From my point of view, it actually sounds really good, and because I'm inside the Hangout, and the people who are inside the Hangout will probably can tell the difference now of what it sounds like. But also, I know there were some audio gaps that happened while Pamela was talking.
I'm reading about this. I love reading.
Yeah.
Fraser was just pretending to be able to hear me.
That's right, right. And this has actually happened since the dawn of the show, which is that we'll have a drop in our connection, and I will just try and get. She's probably talking about this, so I'll just sort of continue on or ask a question or try and connect it together. Because what happens is Pamela records her side locally, and I record my side locally. So we've got nice, good, pristine copies. I guess I don't even need this microphone anymore. I don't even need to talk in this anymore. We both have pristine copies of the audio, and then we mix that together. And so even if there has been drops in audio, then it still sounds as good as it can. But the quality of the video, it's too bad. I really hope that the Hangout people will actually boost up the quality of the video.
Yeah. And part of the reason you're having Hangouts is I'm abusing the Hilton Austin's Wi-Fi system, and I don't think they were quite prepared. The other day after we were done recording, they actually blocked plus.google.com for a little while.
Yeah. And then the other problem that we have is trying to get the sort of word out that we're going to be having the Hangout. That takes us a couple of minutes to kind of get everything organized. So,
like I said, I'm writing software to automate this for us.
Yeah, well, maybe have someone, if someone wanted to, continue with the extension for the better Hangouts, that would be pretty helpful too. So, does anyone have any questions? Because if not, we'll just wrap it up.
Right. I do have a grant to write, sadly.
You have a grant to write, and I have a floor to finish. So John Gallant asks, during the entire show, Fraser was always on a small screen and Pamela was on the larger screen. Will toggling between be done? Only if it's done automatically, because I'm already trying to coordinate 5 different things at the same time, and so I can't act like it's really hard to be a director at the same time. When we do multiple people, the way this works is that you guys see the Hangout from my perspective, and so it never shows my screen because I never need to see my own screen. Now what I can do while I'm recording the Hangout is I can click on my screen or any one of the people that's joined us, and I can make them big. Right, so I can focus the camera just on me, or I can then turn that back off again and then focus it on other people. So this is sort of one of the downsides of the technology, and we're still trying to figure out how to make that work. Yeah. And
we may need to get someone on a third computer to actually produce it.
Right. So what we can do is record the show from the perspective of another computer, and so join the Hangout twice. But then it sort of takes up a slot, and there's some downsides to that as well. So, hey Chuck, how's it going? Oh, we lost you again. Oh well. Yeah. So if anybody wants to jump into the Hangout with us, you can just you can click that link that I posted into the chat. So I don't know if that answered sort of why I'm on the small screen. We're aware it's an issue. This is all such new technology. We're totally beta right now.
We're working on it.
Yeah, well, and I think our theory is really that it's more fun to just play around and just do these things and not worry too much about if it's super high quality. I think you guys appreciate being able to participate in the process as long as you're just not too mean to us, then we're fine.
Yeah.
Any comments and details about Titan? Have you been hearing any buzz about that, Pamela? About the I guess so Jonas Kidan is asking about the I guess the lakes and haze on Titan, right? The fog. Is that right?
This is the wrong meeting for that. So this is all astronomy versus planetary. Where I'm expecting to hear a ton about that is in March. I'll be going to the Lunar and Planetary Sciences Conference down in Houston. And that's where I fully expect to hear all the new news on what's awesome on Titan.
And then James Graytrix asks, I just got a Bushnell 470 by 60 zoom refractor telescope for my niece for Christmas. Is it a crappy model? I've had a hard time finding consumer reviews. So
from what I remember, I haven't looked at the Bushnells in a while. Bushnells are more designed for bird watching and bright light conditions. So they have perfectly good optics, but where they may not necessarily be as good is with really good nighttime amateur astronomy binoculars. You have special overcoatings on the glass that make it more likely that light will pass into the glass rather than reflecting off the surfaces. So if you've ever been in a bright room at night, you can look at a window and see the window act like a mirror. And when that happens, that means some of the light from the room isn't escaping the room. Well, if that window was instead the lens of binoculars, that would mean some of the starlight isn't getting into the binoculars. So with Bushnells, from what I remember, this is memory, I don't know that particular brand, they have really reasonable optics. They just may not have as good an overcoating, but it's a great starter set. So use them until you get sick of them, and then step up, and actually you said telescope, the same thing. That's a spotting scope for birds, I believe. Step up from there to something. Teleview makes good ones in that size. There's several other companies, Celestron's one of my favorites, that make spotting scopes as well that have the overcoatings that you need for astronomy.
I mean, any of these are going to show you Venus, Mars, Jupiter, Saturn, the Moon, some of the brighter...
And that one's good for globular clusters.
Yeah, and some of the brighter deep sky objects. And it's where it's going to... And it's great to just use the gear that you've got until you get sick of it, right?
Yeah.
And the thing that's going to drive you crazy is probably the mount, because you're going to have a really hard time lining something up and then keeping it in your field of view while the Earth is rotating, and so the object is moving in your field of view. And so use stuff and go out and take it out and set it up and look at and show stuff and get to know the night sky. And if you're feeling like, oh God, I really hate how I can't see this or I can't see that or I can't resolve this, then you'll want to look at taking things to the next level. But Bushnell's a pretty good manufacturer. It's if you get really terrible department store telescopes that are just worthless, that's when we recommend you dump them and step up to at least the bottom of the ladder with telescopes.
Right.
So did anyone joining us in the chat have a question for us? Feedback, comments, suggestions, info?
Not allowed to ask any planetary questions, right?
You can ask anything.
You can ask planetary questions. I just may not know the answer. So go ahead and ask.
I'll think of something in a second.
Okay. So Bridget Sheeran asks, is there much being done within astronomy to tackle light pollution? Yeah. I'm quite fed up of pink clouds.
Yeah, no, there's actually, the International Astronomical Union has passed a dark sky resolution, and is working with the United Nations to try and get light pollution ordinances addressed worldwide. They are looking to, in the future, when they determine something to be a UNESCO World Heritage Site, to make it a World Heritage Site, not just because of the fabulous geologic features, the fabulous archaeological features, but also because it's a reserve for the night sky, the reserve for animals. And so it's starting to get recognized at the highest levels of the global community. At local levels, it unfortunately goes community by community. So in Arizona, they have fabulous light ordinances. In Massachusetts, they're starting to pass them as well. So if you're in a community where you're sick of pink clouds, unfortunately, it may be time to start partnering with local lobbying organizations to try and get legislation. Now, if you need help, you can go to the International Dark Sky Association, and they have pathways to help you do this. So there's people on your side, they'll help you, but it's still grassroots, because somewhere between the UN and people everywhere is all the national governments, and we have to really conquer this one national government at a time at a certain level.
I mean, we've got physics on our side, which is that in many cases having a light that points straight down, very directed, either in one of these new LED streetlights or even just a fairly nicely directed light, is both more energy efficient for the city itself and preserves the night sky as well. So it's just a matter of getting people to move to the better methods that have been done. But we can also do this around our own houses. I mean, a lot of people have these globe lights on their driveways and things like that. But you can just, you can walk up to those people and nag them if they're on your street to swap out those things. But I know, people don't like to necessarily confront people directly. So yeah, it's a huge problem, and I have less of a problem here. I mean, I could see the Milky Way from my backyard, which is nice. Let's see. So James said that the instructions said you could see the rings of Saturn, and you were skeptical. No, I'm sure you'd be able to see the rings of Saturn in a telescope.
Yeah, those are really bright.
Yeah, you can see you see the rings of Saturn in almost any kind of telescope, which is our possibly my favorite astronomical wow moment for people. Is like, if they've never looked through a telescope, I'm like, take a look through a telescope and check out Saturn, and they're like, is that a picture? No, you're actually looking at Saturn. It has the rings just like in the pictures.
Yeah, it's really kind of awesome.
Yeah. So does anyone in the group have a question? No? Okay, well, we keep moving. Just jump in any time, people.
Hey, Pamela. I don't know if this is working, but I'm going to try anyway. My first time here and all that, and Fraser, known him for quite some time. I'm the president of the Fraser Valley Astronomers Society. Quite often we do a lot of lectures and what have you. How do you deal with people that say that we didn't go to the moon? Me, I used to just carry a big bat, but anyway.
I one, refer them to Phil Plate's website, because really he is the man on this. Two, I point out astronomers suck at keeping secrets. And when you start thinking about how many people would have had to have been engaged in keeping that, not possible. Three, there were amateur astronomers all over the place that could see the spacecraft on their way there, that tracked them. There was a lunar laser ranging station in Texas that tracked the mission. And now with the Lunar Reconnaissance Orbiter, with Chandrayaan, with Chang'e, with all of these different missions from all of these different nations, many of which don't like us, you can see the spacecraft sitting there on the moon. And I don't think any conspiracy theory in the world could get all of these different nations that only mostly get along, but not completely get along, to all keep the secret and fake data.
That's a good one. Like, don't you think the Chinese would love to humiliate the American spaceflight program? So the one that I always use is the Retroreflector. So during one of the missions, the astronauts drop these mirrors on the surface of the moon, which are then used now by astronomers to accurately target the distance to the moon. And so they fire a laser pulse up at the moon, it bounces off the moon and comes back, and they can know within centimeters the distance of the moon. And that wouldn't work if those retroreflectors hadn't been dropped off on the moon for this exact purpose. So Yeah, no, Paul has got this beautiful dark sky park out in Fraser Valley, which I've been to a couple of times, and it is one of my favorite places to go. It's just beautiful. So if you're ever in the Fraser Valley, check out their dark sky reserve. It's just amazing.
So
Cool.
we can probably take one more question. I'm going to need to head back to the conference, and we will be recording again next Monday.
And Thursday for our space
And
roundup
Thursday
with.
for our roundup, yeah.
Yeah. Anyone have a question for us?
I'll throw one out there.
Question. Okay.
Yeah. How you doing, Pam? We met actually
I'm
at
doing
the STS 129 tweet up launch a while ago.
I remember you.
Great to see you again. So I've been reading recently that there's been a lot of new data coming out about what has been here before the universe, and that apparently there are, in the cosmic background radiation, there's actually, I don't know what to call it even, signs of potential collisions with other universes.
Fossils, basically.
Good word, yeah.
Right.
So what exactly is going on?
I've read the papers. I've read a couple of the papers on this, and from talking to other people who've actually seen the data sets that were utilized, it's a neat idea that if there were other universes, they would have left basically signals within ours that would have certain characteristics, certain symmetries. But you can also get those exact same things if you have image artifacts. And so there are a number of people who are focused on observational work who think that this is actually just image artifacts, that if you process your data a given way, you're always going to see this. And if you process your data a different way, they go away completely. So I really think that it's a great idea by people who are theorists and just don't know how to deal with the actual data as well as they know how to do calculations.
But I mean, that's how it works, right? I mean,
Yeah.
the theorists make predictions, and the observers try and look for them, and if they find them, they look for more confirmation, and that's how science moves forward.
And over the lifetime of the Planck mission, it'll get more and more data that will allow us to see things with higher and higher accuracy, and to hopefully dissuade these poor souls who are working very hard without the lifetime of expertise that they're wrong, or the data will say, no, all the rest of you who called us wrong, well, we actually were right. So it's going to get decided as the data quality goes up.
So it's just too early to tell then at this point?
It's too early to tell. Right now, it does a very good imitation of an image artifact.
Okay, great, thank you.
Cool. All right. Now you got to get back to the conference.
I do.
So why don't we wrap it up again? If you can +1 this episode sort of in the stream while you're doing it. If you haven't already, you probably want to circle me and Pamela in Google+, and that way you'll get notified in the future. It'll pop up in your stream, because if you clicked over from Twitter or Facebook, then you won't get those notifications unless you actually circle us, because that's where it shows up. We're going to probably do some more observing with some other telescopes probably tomorrow night, I think, but we're very random about when we do that. And then the next thing we're going to do is this weekly space roundup on Thursday. So hopefully everyone can join us. And again, we do the same thing. We round up all the stories, and people can ask us questions in the comments, and we have all of your favorite astronomers there. So. And
that's Thursday at noon GMT -6, 10 a.m. Pacific.
That's right.
And so that makes it at, I believe, 5 p.m. London time.
Are you still going to be in Austin for that, or are you back home?
No, I'll be back. I'll be back
Okay.
in St. Louis for that.
Great. Okay, great. All right, well, thanks everybody for joining us. Thanks everybody for watching, and we will see you next week.
Thank you all for being here. Bye-bye.